Taiwan. Today's topic is application of mass spectrometry for analysis. So there is two keywords in this topic. First, I will introduce the mass spectrometry, MS, a powerful technique for molecular identification and widely used in many scientific research areas, including metabolomics, proteomics, microbiota, and so on. And then I will briefly share some cases that the application of MS on food science. So this course, we are not talking about the traditional food analysis. So we are not focused on the principal component analysis, okay? Sorry, the proximal analysis. First, let me introduce myself. I got my PhD degree in food science from National Taiwan University in 2010. I started to contact the MS technology since 2009 for establishing the quality control platform for food. During my postdoctoral career, the Q-TOF was performed to evaluate the therapeutic effects of traditional Chinese medicine by proteomics approach. A linear ion trap was utilized to identify and quantify the secondary metabolites of traditional Chinese medicine by metabolomics study. Nowadays, a photomic study was performed by OB trap to investigate the food authenticity and food safety. There are three different MS machines I just mentioned that, including Q-TOF, linear ion trap, and OB trap. We will see those machines later, okay? So first of all, why MS is famous today in food science? In chemistry area, MS has been used for investigate the ion physics and ion chemistry for many years. But in Taiwan, people pay attention on MS technologies because the food scandal. It should be known that food scandal is not equal to food safety issue. Of course, those food scandals may remind us to focus the quality of food, but not those food will kill you, okay? So in Taiwan, the impressive food scandal is a plasticized drink in 2011. So in 2011, the plasticized was used in drink as emulsifier to making the clouding. In this case, LC-MS, in this course, we are talking about MS, right? So LC-MS was used to detect the contaminated so-called DEHP and plasticized. After this scandal, LC-MS became the famous machine on food-related issue. In 2013, olive oil front has gone viral in news, and again, LC-MS played a role to detect the Cooper chlorophyll, illegally used in oil to pretend the green color. In the same year, the malic anhydride was illegally used in starch to make the good taste in noodles. In 2015, DDT has been detected in handmade drink using LC-MS. In 2016, glyphosate, a pesticide used for GMO soybean, was detected in imported cereal. In 2017, the worldwide issue, eggs contaminated with fipronil, an environment insecticide. LC-MS plays a very excellent role on detecting the pesticides in food. And in 2018, inorganic arsenic has been detected in organic rice due to the environment contamination. LC-ICP-MS acts the excellent role on heavy metal detection. Therefore, if we see the food scandal, LC-MS seems to be a good technology to detect the contamination in food. However, in 2014, the cotton oil scandal demonstrated that detection is not the best way to prevent food scandal, because in this case, either LC-MS or GC-MS, even tandem MS technologies could not find any substantial contaminated in the cotton oil. So for the food scandal, MS technology could be a powerful detection because of the target contaminated can be detected. So the major keyword is target. So if you want to use the MS technologies, first of all, you need a target, or you just like in the 2014 for cotton oil, there is non-target, so the MS may not efficiency. Okay. Safety. The food safety issue has the 7 basic principles by Federal Ministry of Food and Agriculture in Germany, aka BFR. The 7 principal principles, including cooperative responsibility, traceability, official food controls, the precautionary principle, independent scientific risk assessment, separation of risk assessment and the risk management, and the transparent risk communication. The most important is the first principle called cooperation responsibility. So what that means is HACCP and FSSC 22000. That's the basic system control for food safety. So in these 7 principles, MS technologies could give some information in traceability, official control, the precautionary principle, and independent scientific risk assessment. So for food traceability, proteomics or metabolomics performed by MS could give the content of protein or metabolites in food. The official food controls refers to the quality or the regulation of food. So there is a target marker. MS could complete it to detect the level of the target marker. Okay. The precautionary principle is the best way to prevent the food scandal. However, they need a high-resolution MS technologies with the non-target analysis. And the final, the critical role of MS assist the independent scientific risk assessment is to investigate the exposure of contaminated in food. So based on these 7 principles, MS technology is widely used in food science. So therefore, we know that MS may not be a panacea for food safety. MS could not do anything, okay? But MS played a detective to looking for something wrong. If there are something wrong, maybe MS could detect it, but MS is not the panacea. Okay, we can just rely on MS technologies to prevent the food safety. That's because there is a 7 principles. Do you remember? I just mentioned that the first principle is cooperation responsibility, so-called HACCP and FSC 22000. So because MS has a powerful quantitative activity to measure the amount of target marker, such as adulteration, illegal chemicals, pesticide residues, contaminants, and also the quality control marker. So it is very important. MS needs the target marker. I repeatedly mention this word, target. Okay, so if you want to use MS to do anything, you need a target. Because MMR is the only way to qualify and identify the novel compound. But MS only detects the target, which means the known compound. Okay. So let's review the evolution of analytical chemistry. For food analysis, the basic composition, including moisture, proteins, carbohydrate, and lipid, were evaluated by a simple chemical reaction, such as Kyoto for nitrogen determination for proteins. So that's proximate analysis. We are not talking about today. And today, the first electronic portable pH meter was used for lemon maturation. And in 1914, Since 1914, the electronic spectroscopic were used for more detailed analysis, such as UV, IR, and MMR. And the evolution of chromatographic results at the earlier 19th century by Zwitt has a critical role in development of food analysis. So in 1952, GC won the Nobel Chemical Prize, building up the variable tool in aroma and flavor analysis. And later, LC is later than GC. LC made high-resolution separation of complex mixture of non-violet and light. In addition, the MS technologies was raised at 1922 by Aston. The ion trap won the Nobel Physics Prize in 1989. In 2002, the ESI and the MALDI won the Nobel Chemical Prize because the complex mixture can gain the high efficacy on MS. The rise of the modern analytical platform gives us the omics study. So thereby the foodomics study was pointed out today. So we are talking about foodomics study, but if we just use the later analytical machine, we could not do that. But for the modern analytical platform, we could do the omics study to confirm the foodomics. So foodomics, what is foodomics? Foodomics is a discipline that studies the food and the nutrition domain through the application of omics technology. As shown in this graph, there is a global perspective of the knowledge of food. So the aims of the foodomics are the assessment of the food safety and the food authenticity, the study of the mechanism of taste and olfactory sensing, and the biofunctionality of food. So we are talking about food science, and the foodomic study is focused on the food authenticity, food safety, food functionality, of course, the taste and the olfactory sensing. So all of these components is included in food science, right? So according to different approaches, the different technologies were performed. However, the mass spectrometry, MS, is the powerful technology to comprehensively characterize the chemical profile and the use for food safety and the food functionality. In addition, although PCR may provide the genomic study to identify food, the secondary metabolites were affected by the weather, soil nutrient, and many microenvironment. So in my lab, our study wants to use the MS technologies to carry out the food authenticity, but not using PCR. Okay, so we know a food, if the food grows in different area or different region, the composition will different. So if you only use PCR to identify the food, it's not enough today. Okay, but MS could comprehensively characterize the chemical profile. So we want to use MS to do that. How to do that? There is a term of food fingerprint. Food fingerprint is the gene of a food scientist. If there is a fingerprint just like human, we could easily to discrimination the truth one from a fake one, right? If we have a fingerprint. So scientists want to find out which compound could characterize the food, the specific food. So using a specific compound to characterize a specific food. So they point out some chemicals such as chlorogenic acid. They provide chlorogenic acid for some food processes, the hexanol for geographical marker, oleic acid for adulteration, and the ethylene acetate for the deterioration. However, if the single compound could be a marker to distinguish the different food, it is also an easy way to counterfeit, right? For example, if the content of chlorogenic acid is higher in A food, so I can put chlorogenic acid into B food. to mimic a food, right? So if we just use a single compound to characterize the specific food is not enough. Therefore, how to detecting all compound, all chemical compound, all chemical profile is the major mission to establish the fingerprint. Of course, some cases use the pattern recognition and using the mathematical algorithm to identify the specific species, such as microbiome. I will talking about microbiome recognition identification by biotyper later. Okay. So today's course is MS, right? So there is a popular belief that MS is used for the compound identification. However, MS is only used to detect ion information generated from ionization and the mass analyzer. Frankly speaking, MS is an electronic weighting balance to measure the weight of molecule. So let's see how MS data give us what kind of information. From in general MS data, we could gain the major mass by mass to charge ratio, M over Z. So we gain the major mass. If the high resolution MS performed, the isotope pattern will detect it. And the tandem MS technology gives the fragments of target compound. So all the MS data only give the mass to charge information, but not compound identity. So MS only detect the ion information, not the structure. But through the deconvolution process in MS, this process called dereplication reverts to discover the non-natural products by MS data, library search or interpreted of non-mass spectrum fragmentation. So if we use this MS data into a structure, this process is called dereplication. So how could do that? The major mass give the molecule weight depending on the charge state because it's mass to charge. So depend on the charge state. And the molecular weight combined with isotope pattern could predict the element composition, which means how many carbon, how many nitrogen, how many oxygen, how many hydrogen, even the sulfate. We can calculate it by the isotope combined with molecular weight. But they only get the molecular formula, not the structural formula. So we only know the molecular formula, not structure. How could do the structural elucidation? That depends on the MS data. That's because MS data may predict the possible fragment to piece together the structure. Then the compound may be identified. So this process is just like puzzle. So how to puzzle your structure by the independent MS data? It depends on our knowledge. So using MS to identify compound is not an easy way, and also not the official way, because MMR is the Bible for identification. Okay, so if you want to identify novel compound, you should use MMR, but not MS. But MS is very powerful. People may misunderstand the MS technology. That's because most of people believe that MS is a universal detector. Just like Doraemon, you know Doraemon. Doraemon has two magic tools. These two magic tools can easy to detect the material of food or good. That is a very ideal item for me. But for scientists such as Detective Conan, that's impossible. There has not a single machine to detect and food material in an easy way. Impossible. Okay, so we need to combine those data with our knowledge to do the structural elucidation. Okay. Okay, mass spectrometer has four major components, including sample inlet, ion source, mass analyzer, and the detector. Sample inlet means how to inject the sample into the MS. Of course, we could not put an intact apple into MS, right? So the extraction is very important issue. And the sample preparation decide the compounds we can detect it or not, depending on the chemistry of compound structure, such as polarity, molecular size, and so on. So that's why I keep talking about the target. If you want to analyze something, you need to extraction. So which solvent you use will depending on what kind of compound. So if your compound has a higher polarity, you use methanol or ethanol to extract. And then you will not find the low polarity compound, such as violent compound. Okay, so the first step is very important. After the sample preparation and the sample inlet, the key parameters of MS is ion source. Because of MS only detect a chargeability and the electronical gas phase ion. Again, MS only detect the chargeability and the electronical gas phase ion. Ions are generated by inducing either a positive or negative charge in a neutral species. So the expression of molecular detect usually use the N plus or N plus hydrogen plus or N minus hydrogen minus. Okay, so if you want to use MS to detect something, your compound needs with charge. Okay, so MS is not the universal detection, only detect the chargeability and the electronical gas phase ion. So ion source is very important. Another core parameters of MS is the mass analyzer, also set the price of MS. The gas phase ion are electrostatic direct into mass analyzer, where they are separating according to mass to charge M over Z. So mass analyzer is place an electronic weighting balance to measure the M over Z. Okay, so if your compound through sample inlet and ionization, and finally they will analyze with mass analyzer according to mass to charge. Of course, has a detector. So the detector measures the intensity of the ion signal, and then MS determine the abundance and the M over Z of each compound present, which created a mass spectrum. A classic MS spectrum is shown x-axis is M over Z, and the y-axis is relative intensity. In this spectrum, 100% of the peak means the most abundant in this spectrum. So we will call the base peak. Okay, so in this spectrum, this peak is 100%. It's a base peak. Only in this spectrum. Okay. So we are talking about MS has a four major parts. And the first one is sample inlet. They will depending on how you use the how could you inject your sample. So you can use LC, you can use GC, you can use just infusion or use element analyzer EA. So it depends on you. But for MS, the most important is ionization. Ionization is the key parameters of MS because MS only detect a chargeability and an electronic gas phase ion. Oops. So we offline? Sorry. Maybe we have problem. So should we offline? 他们断掉了，那我该怎么办？我该等他们对不对 ？Of course. Okay, for now, there is any question? If you have any question, just raise your hand. Just interrupt me. Okay. 所以他们断掉了，会发生吗？我以为季中，我记得我上次来讲，我有说。 So, hello, Japan. Can you hear me? Hello. So, hi, Japan.
Hi.
The signal from Taiwan. It's okay.
It's okay. Thank you.
So let's start the course since page 11. Okay. So we just mentioned that MS has 4 major components, including sample inlet, ion source, mass analyzer, and the detector. And the annihilation is the key parameters of MS because of MS only detect the chargeability and the electronical gas phase ion. So the process of transforming a neutral species into a gas phase ion, which charge called annihilation. So if you want to detect a compound, you need let your compound with neutral species into a charged state. So that's called ionization. So there are many ionization could be used depending on the compound polarity. The earlier ionization is EI, electronic impact ionization. EI uses the high energy 17 electron voltage to impact the structure to forming the positive charge. However, the 17 electron charge is too higher for covalent bond. Thereby, the fragment will occur. So EI is the hard ionization. So for hard ionization, it's called the ionization will cause the compound fragment. So it's called hard. Okay. In order to gain the molecular ion, but not only the fragment, the EI is modified into CI, chemical ionization, which use the gas. Therefore, CI could gain the intake molecular ion. So CI is the soft ionization compared to the hard ionization. Okay, and the APCI is more popular use instead of CI because APCI could perform in LC liquid chromatograph. Okay, so if you want to use LC-MS, you should not use EI or CI. You should use APCI or later. Okay, in fact, there has the LCEI right now today. Okay, but it's another story. And in 2002, the Nobel Prize in Chemistry awarded the MALDI and the ESI, both used for macromolecules such as protein. So for MALDI, Tanaka Sensei developed the matrix-assisted laser desorption ionization (MALDI) by using glycerol as a matrix and using laser as energy. So MALDI could detect the intake sample, of course, only the surface. Okay, and the Professor John Finn developed the electron spread ionization (ESI). Is widely used in LC-MS. Nowadays, many other ionization has been developed in order to overcome different samples or compounds. So how to choose the suitable ionization? It depends on your target compound. If your target compound is lower polarity, lower polarity here, EI and CI is useful. But if your compound is higher polarity, the ESI is the best choice. And if the lower polarity compounds could retain in LC, the APCI can be used. Finally, if you want to analyze the intake protein, such as the gel from SDS page, the MALDI is powerful ionization for protein detection. So from the ionization, we could easily know that MS is to detect the target compound because ionization is depending on what you want to detect. Different compound has different polarity, so you need to use different ionization to perform the MS technology. Okay, so ionization is the first. And then mass analyzer. Mass analyzer is a core parameters of MS. Different mass analyzer has different function, but the principle is the same. Is how to measure the molecular weight is according to the Newton's secondary law of motion, F equal to ma. So which means the mass moving state is related with the force. So you get a force, the molecule will acceleration with the moving. Okay, so A is the acceleration. So the first MS is developed by J.J. Thomson. J.J. Thomson to evaluate the mass to charge and then measure the isotope of each element. The driving force is magnetic. So you need a force, remember that? So for J.J. Thomson, the driving force is magnetic. Because MS only detect the electronic ion, So the iron will with charge will affected by magnet, and the lighter is easily the effect. So magnetic could separate it lighter and heavier. Okay. In 1946, time of flight, aka TOF, has been developed. TOF is to measure the flight time in a vacuum linear tube. So small molecule move faster than the large molecule. Okay. The Nobel Prize in 1989 award to the iron trap, which the driving force is voltage. So we are talking about different driving force. One is magnetic, another is voltage. Okay. So in 1977, triple quadruple and tandem MS technology has been developed and widely used today to detect the target compounds such as pesticide or additives. Okay. The hybrid MS technology has been developed in 1984 to combine the quadruple and the TOF to be a high-resolution MS technology called QTOF. In 2000 year, Mark Rolfe developed the OB trap, the high-resolution MS, which the driving force is voltage. So we know for mass analyzer, they need the driving force. Both magnetic or electron field are two major forces to keep the ion moving. And then the detector can measure the time, frequency, or space to determine the mass to charge ratio. Okay, so mass analyzer is very simple. You get the force and you measure the acceleration. The force including magnetic or voltage. The acceleration could be detected in time, frequency, and the space. Okay. Of course, there are other MS analyzers such as ICR, but we are not mentioned in this course. Okay, there has many MS analyzers here today. So back to mass spectrometry. Now we know the mass technology is comprised of 4 components, including sample inlet, ion source, mass analyzer, and the detector. Therefore, only LC mass, this word, may not enough information on mass technology. The term of LC MS could be divided into 3 parts: inlet, annihilation, and the mass analyzer. For example, LC ESI QTOF means the inlet is LC, the ion source is ESI, and the mass analyzer is QTOF, a hybrid high-resolution MS. And the GC MS may be reversed to GC APCI triple quadruple. So the inlet is GC, ion source is APCI, and the mass analyzer is triple quadruple. It's a low resolution tandem MS. If you want to detect the inorganic or heavy metal compounds, the ICP MS is used. Reverse to the annihilation is ICP, inductive coupled plasma. And the mass analyzer is single quadruple. So the inlet is direct infusion or injection. Okay. So there are many different components used in mass technologies. So after this course, we could describe the mass technology more clear. So we're not talking about LC MS again. We talk about LC ESI triple quadruple or LC ESI QTOF. Okay. Okay. So for mass technologies, there has a regulation after application. Okay. So if we want to use if we want to use mass technology to do the structure, we need the regulation. So the common regulation is SAND 11813/2017. So if you want to use MS technologies, we can divide it into two different parts depending on mass analyzer. So one analyzer is accurate mass, is high resolution, and another mass is unit MS, low resolution. Okay, so according to the regulation, the MS technology could divide into unit mass or accurate mass. The resolution lower than 10,000 called unit MS, which means the accuracy of molecular weight in single digit, such as we just calculate 1, 2, 3. Okay, but accurate MS defined as a resolution is higher than 10,000. Therefore, the accurate molecular weight could be more than 2-dimension digital, such as 123.45. So for unit MS, we just okay. There are very different algorithms, different logic on these two different MS technologies. The principle is fragment. We need to know the characterized fragment to representing the structure. So if you want to do the MS technology to detect the structure, you need the fragmentation of the target structure. So they require two transition pair, one precursor ion and two product ion. So two transition. The most of MS technology used in food science is triple quadruple. It's the unit MS. Okay, triple quadruple also the official quantitative method in many country legislation. Okay, so the low resolution triple quadruple used for identification such as illegally additives or pesticides in food. Another unit MS is ion trap, ion trap, which also can generate the fragment. However, ion trap only used for the quantitative because the duty cycle is longer. So IT could not measure. IT only could measure less compound, but has more matrix effect. So if you want to quantitative compound, you use triple quadruple. If you just want to qualitative the compound identification, you could use the ion trap. Okay. So if recently, accurate MS rise and accurate MS gives the accuracy molecular weight and the isotope pattern. So therefore, we could predict the structural formula. So for accurate MS, the accuracy molecular weight is very important with the isotope pattern, okay? Because we can get the formula. Combined with the hybrid technologies, which means use different MS mass analyzer into a machine. Accurate MS has both qualitative and quantitative activity on food analysis. Okay, so both these two types MS technologies could be used in food science. So the fundamental of MS just mentioned that. So let's see how the MS could do that. So the application of MS on food analysis. First example is the food additives. In this study, we have the target compound. Okay, for MS technology, you need a target compound. So if we have a target compound, we could use the unit MS to confirm whether the target compound exists in food or not by the two transmission pair. Remember that two transmission pair. In this case, the target molecule of methyl paraben is 152. After ionization in negative mode, the molecular ion presents as loss of hydrogen. So the molecular weight is 151, right? After correction, during tandem MS, they can generate two fragments, 136 and 92. Accordingly, we have two transition pair to identify the methyl paraben use 151 to 92 and 151 to 136. So we can see the MRM transmission pair 151 to the 92 and the 151 to the 136. That means two transition pair. So it's a very useful and routine analysis for food additives using tandem MS technologies. Okay, so it's easy way. Use the unit MS to detect the target compound. Another example is for the phytochemical identification. We all want to know what or how you want to do that information. In this case, because we want to know all of the compound, so we don't have target. Instead, the accurate MS need to identify the compound with the accurate mass and the fragment. Okay, so we combine the accurate mass and the fragment, we can identify compound. Therefore, each accurate mass, which means the molecular weight, could calculate 2-dimension digital, right? So for this sample, if we just use the unit MS, we got 459 only. It's not enough to calculate the element composition. So if you use the accurate MS, we could calculate 459.09. That combined with the isotope pattern will help us to calculate the element composition to gain the formula. So it's very difficult way, right? It's very complex. That is a way to generate the phytochemical fingerprint for discriminating the process of the raw material. So in this paper, they use the high-resolution MS to identify the raw material and the process material by using the fingerprinting. Okay, that's a case. Another case is biotyper. Biotyper is an official method for microbial identification approved by LAC. Biotyper is based on the multi-top MS technologies to collect the fingerprint of microbial peptides. According to the database, if the experimental fingerprint fit the reference database, we could identify the possible microbiome in a rapid and easy way. Okay, we just put the sample in a spot and analyze by multi-top. They will gain the fingerprint. So if the fingerprint is just fit the database, we can identify. Of course, the premise is the analyzed microbiome has a record in the database. So therefore, if the microbiome is a novel microbiome, it cannot be detected by biotyper. Okay, that's because biotyper only use the reference data. So again, MS only detect the target. Another application is for pharmaceutical. For pharmaceuticals such as PK or PD, we need to know the metabolites generated after digestion in organism. So if we eat something, they will metabolize. They will has metabolized by metabolism, right? So accurate MS could find out the unknown compounds. So unknown metabolites from the target compound could be identified by accurate MS. In this case, MS is not detect the unknown. The unknown comes from the target compound. Okay, so we have a target compound. We just want to know whether the metabolism to affect the target compound into the metabolites. So MS could do that. So how could do that? The accurate MS, isotope pattern, and fragments are important information for identify. So in this case, this compound is uric acid. If uric acid has a molecular ion is 193.04. Of course, 193.049 is okay. Therefore, the metabolite may contain a glucuronide or sulfate during metabolism, right? So during metabolism, the target compound will added with glucuronide or sulfinic during metabolism. So we could find the higher priority compound which contain the molecular fragment here. So this compound, M6 and the M8 compound, contain a fragment with 193.049. And this fragment just equal to the uric acid. So we may predict this compound is a metabolite from uric acid. So if you want to use MS to do this experiment, first of all, you need the target. And then you need to know what kind of metabolism will occur, such as glucuronide or sulfate, okay, or other metabolism is possible. So it's very useful for PK and PD experiment. And the very interesting study I will show today is to evaluate the food consumption named metabolomics to characterize dietary exposure study, MED study. The MED study is designed to discover whether metabolics could be a way, a non-subjective tool to characterize what people eat without need the diary or questionnaire. So for traditional way, if you want to know what people eat yesterday, you need people to write the dietary or you give the questionnaire and they will fill in. But in fact, people don't remember what you need, right? So I just can remember what I ate yesterday morning. So in that case, MS may provide another way. So it's an interesting study called MED study. So MED study is a design experiment. So first step, the fasted participant consume specific food, and then the metabolism fingerprinting representing postprandial urine was then generated by non-target mass technologies. And then the PCA, principal component analysis, showed the different diet could be discriminated from the standard diet by chemical fingerprinting of urine. Furthermore, the highlight target could identify by accurate MS to indicating the signal as a biomarker of specific food. For example, in their study, okay, they found aniserin is a candidate biomarker for oil fish consumption, and the proline betaline for citrus food. Okay, so another experiment is designed to investigate the habitude consumption of specific food. So if you like to drink coffee, in your urine, you will detect the higher content of dihydrocaffeinic acid 3O glucuronide. It's a metabolite of caffeinic acid. Okay, if you like to eat tomato, the sulfuric acid will detect it in your urine. So this is very interesting study to mimic the questionnaire to understand what kind of food people eat or how many of food people eat. Okay, it's very interesting data. If you are interested, you can find the paper here. Okay, those are the application of the MS technologies I just mentioned. So now I will share some authenticities of food in my study. The authentication of food is one of my research interests. That's because different food has different economic issue. And also for Taiwan, we all like food made in Taiwan, but not food in Vietnam or Philippines, right? I'm not sure. So it's very interesting study. Today I will show the Amaranthia. The Amaranthia family was the target grain in this study. So there has several species in Amaranthia, including amaranth, quinoa, and the julius. These grains form nutrient and has better tolerance on environment, which can be favorable as food consumption. Amaranth major yield in Mexico, quinoa major produced by South American, and the julius was originally produced in Taiwan. According to the appearance, the beautiful red color was similar to this grain, right? But for economic issue, the different source of this grain should be identified. Therefore, we focus on the authenticity of julius in Taiwan. So how could do that? We using the metabolomics study. So after solvent extraction, remember that if you want to analyze, you need solvent extraction. So that is first step. After solvent extraction, the LC-MS technology was applied, and there has two strategies can be used, including non-target analysis and target analysis. For non-target analysis, the four chromato grains were aligned and then extract the peak information. After the principal component analysis, PCA was performed to discriminate this grain by the extracted result. The representing compounds may be identified by MS spectrum. And the other way is target analysis. Target compound will identify first, and then each grain extract will quantitative according to the target compound. In this case, I use another analysis to do the discrimination. So I just want to make an authenticity of julius differ from other Amaranthia family. So fingerprinting first. After the accurate MS analysis, the whole chromatogram can be a chemical fingerprint of a sample. So in my study, both positive or negative mode were used. So sample is QC. QC, which means it's combination of all samples such as julius, red quinoa, white quinoa, and amaranth. According to the chromatogram, we may observe that amaranth is very different from other compounds, right? Sorry, other food. But for julius or quinoa, they're just very similar. And for red quinoa and white quinoa, they are appearance the same. So how could I discriminate those compounds? We need the mathematical algorithm to do the chemometrics. Result of the simple chemometrics called principal component analysis, PCA. PCA is an unsupervised pattern recognition method to detect the intrinsic clustering. After 622 parameters were put together to perform the analysis, the score plot showed the separation between amaranth and other sample by PC1. And the PC2 can separate julius and quinoa, but red quinoa and white quinoa cannot distinguish in this study. So according to the score plot, we can look at the loading plot. The loading plot will show the characterized compounds may be selected based on the result of score plot. For example, these compounds choose due to PC1 representing the amaranth, right? PC1 is amaranth. And the down region of the PC2, the level of this compound is measured in julius, and this compound is measured in quinoa. So we can pick the information from the loading plot. So we pick this information and then we need to identification. This table shows the selected compounds according to the PCA. Even we have the high resolution MS, it is very difficult to identify all compounds. So we only have 3 candidate compounds may be used for discrimination, juries, and the quinoa. So we just can use these compounds, but there has some compounds still unknown. Even I use the high resolution accurate MS. Why the data could not all the compound is identified? That's because the limited by database. For food, there has a very limited database for food-based metabolite, so it's not an easy way to identify all compounds. But we can still know these 3 grains has difference in chemical fingerprint. Okay, but only I cannot know the compounds, but we can distinguish. But it's not enough for me because we need to know the compounds. Why the compound is so important? Not because the compound could be the quality control parameters for food. So I need the compound and I need the quantitative. So in this experiment, we use the target analysis. So first of all, for target analysis, we need a target. So what kind of target? The beautiful red color in juries has a red color, right? So I choose the beta sensing. It's different from anthocyanin. Okay, it's beta sensing. So the MS technologies could be performed to find out the beta sensing in juries. So in this case, we could find 8 beta sensing in the juries. So we could separate each compound and the identification. Of course, we can quantitation the compound, the level of the beta sensing to be a parameters for agricultural quality control. So how could I do this identification? It's based on this slide. So if you want to use MS technologies to identify compounds, this slide may help for you. Okay, so the replication strategy is shown in this slide. That's my replication strategy. So first is UV spectrum. That's because the UV visible spectrum could check the chemical properties according to the chromophore. Okay, so if I'm looking for a color compound, they need a chromophore. So I can to detail the chromophore spectrum. And the red shift, if the chromophore has a red shift means the acetylation occurred. Okay, so if my compound compared to a reference compound have a red shift, I know this compound has acetylation. That's the first. And the second, I need substantial compounds by the accurate MS with the isotope pattern to calculate the element composition. So I need the formula. If I have the formula and I have the UV spectrum, I may predict some compounds here. So in this case, I predict this compound is amaranthine with the molecular weight is 727. The next step is use MS technology to do the mass, of course, the tandem mass technology. So I can find the fragment. So in this case, the fragment from 727 has 551. Okay, and I pick the 551 to do the MS fragment again. They will generate 389. And if I use the 389 to do the MS again, I will generate the fingerprint of the fragment. So in this case, I do the tandem MS technology by using ion trap. It's a low resolution MS technology. So I could get the fragment information from the MS technology. And I piece this information together to puzzle the structure. So I know each peak information and I know the formula, so I can piece this information together. After that, I will do the high resolution MS to confirm the molecular weight. That's because unit MS such as ion trap only detect 7 to 7. But for high resolution, they can detect 7 to 7.18. For the accurate MS with the isotope pattern, I could confirm the element composition. And then I confirm the represented fragment such as 551 and 398. Sorry, 389. So according to this spectrum, I predict this compound is Amaranthia, and of course with a UV spectrum. Okay, so I think it's a very difficult way to do the MS technology to perform. So if we could replicate lost MS spectrum, we could use MS technology to identify compound. If we could not use this information to do that, it's not an easy way. Okay, so people always say that MS is a powerful technology for compound identification. I'm not sure it's easy or not. Okay, so for another target for juries is the beta test. The beta test of juries comes from triterpenoid saponin. So my study also focused on a comprehensive profiling of triterpenoid saponin by high-resolution mass as a tool for quality control in agriculture. That's because if the higher content of the triterpene saponin will has the beta test, and if the lower content of the triterpene saponin, the beta test will disappear. But the biofunctionality of the triterpene saponin is immunomodulation. So if the agricultural food is used for functional food, we need the bioactive compound such as triterpene saponin. So we could not let the triterpene saponin disappear, right? So it's the different strategy, different approaches of food. So I just want to use the comprehensive profile to identify or to do the quality control in agriculture. So in this study, 69 saponin were identified, of course, according to the AQMS, isotope pattern, mass technology, mass fragment acquired by AQMS in a single run. So how could I identify lost compounds? It's relied on this slide. So the compound identification using MS, just like a puzzle, right? We piece the information together to build up the compound. So we need to know which compound is representing molecular weight. So it's a very interesting data in this spectrum. So which is the molecular weight? Is here? No. This peak is the base peak with the higher abundance of ion signal in the MS spectrum, but not the molecular weight of my target compound. The molecular weight is here. So it's very, very lower abundant, right? So the first things we need to overcome is to find out which one is our target molecular weight. And then we have the fragment. So if we know this is the target molecular weight, we found that has a fragment here, here, and here. That means the structure will fragment by MS technologies, and of course the tandem MS technologies. So if we calculated this loss of molecular weight, we could calculate this loss is 162. 162 is equal to hexoside. And of course, they have 3 hexoside. So this compound has 3 hexoside here. And the backbone here. The backbone molecular weight with the isotope pattern I can calculate the element composition. So I have the element composition. I can predict the structure. So I predict the structure is here with the 3 glucoside. Okay. I know it's not an easy way. So the sorry. To sum up, it's not an easy way to identify compound. Only use MS technologies. If you really want to know what kind of, that's not a simple way, I know. And then after the compound identification, the molecular networking should be used to confirm the structural relationship between each spectrum. I just mentioned that the triterpenoid saponin, but different triterpenoid saponin has the backbone, right? So for MS spectrum, the backbone needs similar. So we need to use the molecular networking to confirm that. Okay, so we could confirm those backbones are very similar in MS spectrum. Of course, use the software. Okay, so we know this compound, that's PA, is very similar. The spectrum is very similar here. So those compounds are PA. Maybe is correct. I say maybe. That's because I do not use MMR to confirm that. I just use MS technology and the reasonable molecular networking to confirm my identification. After each compound were identified, the content of each compound could be quantitated. So for this experiment, Julius has the novel compound here. These 2 compounds is very unique compound. Not because for quinoa they have no these 2 compounds here, right? But for the red quinoa and the white quinoa, the red quinoa has these 2 compounds here. It's very different from white quinoa. So for this experiment, I can distinguish the Julius from quinoa by these 2 compounds, and also the red quinoa and the white quinoa by these 2 compounds. Okay, so it's not only the fingerprint, but also the target compounds could be could be the authenticity of food during MS technology. So we can combine all technology together, not only use the target or not only for non-target. We can combine all the MS technology together to perform the experiment. Okay. Okay. Since MS is a powerful modern analytical instrument, but the strategy is more important than the instrument. So which means human brains need win the machine. Okay. MS is very stupid machine. We need use a reliable strategy to identify our compound. So this slide is shown different purpose you want to do. If you want to do is a target or is a routine analysis, the GCMS or LCMS with the standard could do that. So if you have a standard, you can use the MS technology to elucidate the representing fragment of the standard. And then you can use the uni-MS to do that. So it's a target analysis. So you need a standard. If you want to do the non-target analysis, the accurate MS and the database is needed. That's because you need accurate MS with the isotope pattern to calculate the element composition to gain the formula. And then the MS technology will give the fragment. And finally, you need a database to confirm your structure is exists or not. Okay, so for non-target, you need accurate MS. And for a difficult analysis, for the unknown analysis, I'm not sure for now unknown analysis is possible or not. But for chemicals, for chemistry, maybe the aqueous MS and the parent plasma ion may be useful. And of course, they need a chemical joint software. They need to predict each element and each covalent bond, each functional group is possible to predict the compound. So for mass spectrometry for food analysis, depends on what you want to do. If you want to do is target, it's very easy way. You need a sensor and an easy machine of MS. Any MS could do that. But if you want to do the non-target analysis, you need accurate MS. That means high resolution MS, and maybe a library. Okay, so this slide is the Bible of the MS technology application. Okay. Okay. I simply the MS technology used in the food science. So any question? Any question or any slide I need to repeat or to confirm? So any question? No? So any question from Japan? No? Is that okay? Okay. If you have any question, you can email me. Okay. I have an email here. You can email and I will answer you any question if you want to know. If not, I think we could dismiss. Thank you.